Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Then the final speaker this afternoon is going to be David Harvey, who will speak on counting points on projective hypersurfaces.
Thanks very much. So good afternoon, and many thanks to the organizers for inviting me to speak here. Yesterday morning I ran into Pierre Gaudry, and I said to him, I'm a bit worried about my talk. It doesn't have much to do with elliptic curves or cryptography. And he immediately said, great. So I suppose if he was already, sick of talks on elliptic curves and cryptography yesterday morning after 11 talks, hopefully this is a breath of fresh air. So here's contents of what I'll be talking about. First of all, I'll mention some previous results relevant to the main thing I'll be talking about. And then I will state approximately what the main result is. It's a statement that a certain point counting problem can be solved within a certain running time. Then I'll give some computational examples, so some surfaces whose points I have counted with an implementation. And then finally, I will give a sketch of the algorithm, just a very broad overview. So let me set some notation. P will denote a prime, Q a power of P, so P to the A, where A is usually 1, but it doesn't have to be. X denotes some variety over FQ. I'll state more precisely what I need a bit later on. Z sub X denotes the zeta function of X. So this is a generating function encoding the number of points of X over all finite extensions of FQ. And the reason, of course, that we like this zeta function is that it satisfies lots of nice properties. One part of this is part of the Weil conjectures says that the zeta function is actually a rational function. And computationally, this is interesting because it says that the zeta function is determined by finitely many of the coefficients. So if you have bounds on the numerator and denominator of the zeta function, then it says you only have to count the first couple of you only have to perform the first couple of point counts, and all the rest are determined by those. Now, the goal of this talk, of this algorithm I want to tell you about, is to compute the zeta function efficiently when P is large. And what I mean by large depends on the type of variety. I mean, for the types of varieties I'm interested in, larger than has been previously feasible. So certainly not polynomial in log P. That would be nice, but I don't know how to do that yet, if ever. So first of all, we've heard a lot about Scurf's algorithm and its descendants. So this running time bounds, this is log Q to something polynomial in G for a curve of genus G. I actually don't know if this is the most I don't know the most general result, but I have a feeling that something like this is probably true. Maybe you need projective curve or something. But this is roughly what the shape of all these results looks like. Something polynomial log Q for a fixed genus, and then varying badly with the genus, exponentially with the genus, or possibly doubly exponentially with the genus. So if you fix G, this is the best known approach for large P. And we've heard discussed some examples, genus 1 and genus 2. So genus 1, there's this new record has been set recently by Andrew Sutherland, who counted the points on an elliptic curve over a prime field with 5,000, where P has 5,000 decimal digits. For genus 2, we have work of Gaudry and Schoest, who have produced cryptographically interesting sizes of curves, been able to count points on these. I don't know of any implementations for genus 3 or more. Does anyone know if they exist? OK, so maybe no one's done it. I get the feeling that genus 3, maybe you could still do it, but it's become a lot less interesting cryptographically because there are all these attacks on curves of genus 3 or higher. For higher dimensional varieties, I don't know of any general results. So for abelian varieties, you do the same thing as with curves. Curves, you're just looking at Jacobians, so the same thing works there. In general, I don't know of any sort of L-adic results. Perhaps this stuff that Scurf mentioned on Edixhoven's work on modular forms of high weight, maybe that has implications for certain varieties, but I don't know any details of that. So in this talk, I'm mainly interested in higher dimensional stuff. So I'm going to leave this behind and tell you briefly about Alan Lauder's algorithm from a couple of years ago. This is a so-called deformation method. And so we're working with a smooth hypersurface X in Pn of degree d. And this is the setting I'll be working with most of this talk. These are the varieties I'm interested in. And the running time is something like the following. So if you fix P, think of P as small and fixed, then it's polynomial in the size of the input. The size of the input here is the number of coefficients you need to write down the defining equation for X. So some polynomial f of degree d in n+1 variables. So d to the n a so d to the n log q bits is what you need to write down the problem. On the other hand, if you look at the dependence in P, you find it's something like P squared. And that contribution is independent of the dimension. And that's really important because previous p-adic algorithms, the dependency was more like P to the n. So for example, there's an algorithm a few years earlier of Lauder and Daching 1 where the complexity was P to the n. And that's a sort of common feature because you have to work with these power series in n+1 variables with degree something like P. And these dense power series have P to the n terms. You can't avoid it. So this P squared was quite an improvement, and it's conceivable that you could handle reasonably large P with this algorithm. Certainly not polynomial log P, but you still could handle fairly large P. So going back to Kedlayer's algorithm, which really started this industry of p-adic point counting, using Monsky-Washnitzer cohomology, he gave an algorithm for counting points on hyperelliptic curves of genus G with the following running time. Again, this is polynomial in the input data with a p to the 1. And the 1 is essentially happening because it's a variety of dimension 1, because you're dealing with power series essentially dense in one variable. So half of my PhD thesis was about a modification of Kedlayer's algorithm which gets this down to square root of p. And you'll see in this talk some idea of where this square root of p comes from. And the rest of the running time is still polynomial in the input size. The exponents are a bit worse than Kedlayer's algorithm, but it's still of this shape. And then after I did this, Minzlaff did the same thing for superelliptic curves, following the adaptation of Kedlayer's algorithm by Gaudry and Gurel. And just to give you an idea of what's feasible with this algorithm, so for a genus 3 hyperelliptic curve with p about 3 times 10 to the 16, so that's something like 55 bits or something, that takes about a day on a single CPU. So that's accessible. So after I'd worked on this, I mean, it was pretty clear that the superelliptic case would be okay. It looks essentially the form of the equation is much the same, and I was really curious whether you could get this square root of p for a broader class of varieties. And I wrote a proposal on this to the NSF, which was rejected, unfortunately. And after it was rejected, I realized, the thing I proposed, all the things I proposed in this proposal were subsumed in the thing I'm about to tell you about. So I wish I'd known that a little earlier. But anyway, so here's the setup for today. Same as Lauder's algorithm. Take a smooth variety X defined by a single polynomial f of degree d. So it turns out that the zeta function has the following form. You have the sort of standard 1 over 1 minus qt terms, and then you have this interesting part, a polynomial p of t. This is some characteristic polynomial of Frobenius, and it appears in the numerator or denominator depending on the parity of n. So for example, the simplest case we all know for an elliptic curve, so n is 2, you have a curve, a hypersurface in P2, which is a curve, and you have this p of t, which is the x squared minus tx plus p or plus q, and then in the denominator you have 1 minus t, 1 minus qt. So that's what we're familiar with. So p of t is a polynomial integer coefficient, and that's what we want to compute. So here's an approximate statement of the theorem. I've given a similar talk twice before, earlier this year, and the theorem changes every time. So I still haven't settled on the final form. This one is a little more informative than the one I gave last time, but I should say that there's a term missing which I'm not going to write down because it's only polylogarithmic in p. And I'm interested in what happens when p is large. So you should think of everything in this talk that p has, for all the statements to be true, p has to be bigger than some function of all these other variables. So think of p as much larger. So here's the statement. So assume that x satisfies a certain smoothness condition. I need slightly more than smooth. I'll say what that is in a moment. Then I can compute this p of t to n significant p-adic digits, and I'll say what I mean by that in a moment. in the following time bound. So first of all, the square root of p, independent of the dimension. So this is nice. This is what I was hoping for. Then something polynomial in the input size. This is also really nice. This last term is not so nice, this n to the n. And in fact, you'll see this is what kills us in some of the larger examples that I attempted. And I'd love to get rid of that, and I have some ideas, but nothing concrete. So if you want the whole zeta function, you need to take n to be about d to the na. That's about how big the coefficients of the zeta function can get. And you get the following running time bound for the whole zeta function. So square root of p, and then something like d to the n squared, and then something like a to the n. So it's no longer polynomial in the input size. It's more like polynomial. It's more like input size to the n. So that's not good, but that's the best I have at the moment if I want this square root of p. So let me say what I mean by significant digits. So in this setting of hypersurfaces, there is something called the Hodge polygon. So this is familiar for elliptic curves. You have x squared minus tx plus q. And what's going on is that last term is forced to be divisible by some powers of p. And something similar happens for hypersurfaces. There's certain, you know a priori that certain coefficients of p of t have to be divisible by certain powers of p. This is coming from p-adic Hodge theory. So what I mean by n significant digits is I mean you take what you know has to be divisible from the Hodge polygon and add n more digits above that. That's what I mean. Okay, let me say what this smoothness condition is. So let's take any subset of the variables s. So a subset of the integers from 0 up to n. I think of it as a subset of the variables. And I define this generalized Jacobian ideal, J sub s. So the simplest case where s is the whole, it contains all the variables, then this is just the usual Jacobian ideal generated by the partial derivatives of f. But for variables not in s, I have to throw in this extra variable, xi times the partial derivative. Now I'll just add here, just as an aside, I'm not really interested in the case that p divides d, because remember that d is small. D is like 3 or 4 or 5 or something, and p is enormous. P is a million. So this will never actually happen, but the theory all still works if it does, I think. You just need to work with a different Jacobian ideal. You need to throw in f. You don't have f in there for free. And the algorithm still works. I'm not entirely sure about the complexity. The reason it's tricky is that in this case, this nice simple case where p doesn't divide d, then the Hilbert series of this ideal is very nice. There's nice classical theorems that tell you what it looks like. In this case, it looks a bit funny. There's a theorem Macaulay which fails in this case, and the Hilbert series looks funny, and maybe I need monomials of higher degree in the algorithm, and I haven't got the final answer on that yet. So if anyone knows about this, I'd love to know where to read about this properly, because I'm sure someone's figured it out already. Okay, so I've defined, so from now on, p does not divide d. P does not divide d. Okay, so we have this Jacobian ideal, and here is the condition. I need there to be some set S, so some subset of the variables, with at most d variables, such that the scheme defined by this ideal is empty. So the simplest case is if d is more than n, so for example, a degree for hypersurface in P3, that's quite a natural case to look at, then I can take S to be all the variables, so that has less than or equal to d, has less than or equal to d variables, and all I'm requiring is that x is smooth. So if d is more than n, the condition is just x is smooth, that's it. If d is less than or equal to n, there's something else, and there's a geometric interpretation. It's as follows: for all subsets T containing S, the intersection of x with the coordinate hyperplanes defined by the variables not in T is smooth. So for example, suppose I take a degree 3 hypersurface in P3, then I'm asking there must be some hyperplane, some coordinate hyperplane that intersects smoothly with this variety. Now, this is not a serious condition, right? I mean, of course, you can make a rational change of coordinates. So all we're asking in that example is that there is some hyperplane that intersects the variety smoothly. And I'm pretty sure that as long as p is not too small, you can obviously find one. I mean, there are so many hyperplanes. There's got to be something smooth out there. If p is too small, if p is 2 or 3 maybe, I'm not entirely sure what happens. I've tried playing around some examples and haven't convinced myself that there are examples that you can't do this. But maybe there are. So that's something else I have to look into. But in any case, p is large, so I don't care. It's not a serious condition. Okay, so let me tell you about some examples of this algorithm in action. So in February this year, I wrote a toy implementation when I first had the idea for this algorithm. I wrote this in Sage, and I presented some. So I think there's a few people who saw my talk on this in the p-adic methods workshop in Oxford and the point counting workshop at CRM in Montreal. And I gave you some examples of what I computed with that first implementation. So since then, I've written a second implementation from scratch using more efficient everything, some smarter stuff going on inside, but still in Sage. And I'll give you several examples of what I've computed the last few weeks using this implementation. So this is running on a 16-core Opteron server with 96 gigs of RAM, which used to seem like a lot, and now I'm always feeling squished. It's a lot of memory, but anyway. And I've also started work on a lower level NTL implementation, but that will be that's still a few months off, I think.
When you say Sage, you mean Python or?
Yeah, I mean, yeah, just working in Sage, just using data types for polynomials and matrices, and occasionally, well, so what actually happened is when I started work on this, I ran into some performance problems, like obvious performance problems that needed to be fixed. And I made a list of track tickets. As William showed, you can submit bug reports. So I submitted maybe 10 bug reports about things that needed to be fixed up and example timings. And I think most of them have actually been fixed now, I think mostly by David Rowe. Not all the patches are in Sage yet. I think some of them are. But the problem is that as soon as this happened, I needed to get my work done. So, of course, I worked around these problems. And my code became disgusting and ugly as a result. But I worked around them and sort of managed to get it going faster. But I haven't gone back to re-engineer, to un-uglify them now that the code is better. So this is a problem with Sage, is it moves fast, but not fast enough. I mean, I feel like these are all things I could fix myself, right? Assuming I had a few days to sit there and do it. But I just didn't. Okay. So here's the first interesting example. So random degree 4 surface in P3. So by random, I mean I just wrote down all the monomials of degree 4 in 4 variables and chose random coefficients out of FP. And with overwhelming probability, this is a smooth surface. So these are K3 surfaces over a prime field. It turns out that P of t is a degree 21 polynomial, so it's got a lot of coefficients you need to compute. You really only need the first 10, because there's some symmetry that gives you the other half. And I use 2 digits of precision. This is okay as long as p is not too small. If p is less than, I think 43, so about twice this degree, then you would start needing extra digits, because the coefficients are getting large relative to p. And in fact, I think you only need 1 plus epsilon digits. So an interesting question is whether you could do this with 1 digit and somehow pick up the other information by some other means. Maybe some kind of L-adic computation. If someone knows how to do it, maybe even just mod 2 or mod 3. Maybe that's enough. Anyway, haven't looked at that at all. So here's some running times, going from p is 1,000 up to p is 1,000,000. And all of these ran on 12 cores, except for the last one I started running out of memory, and I needed to go down to 6 cores. I mean, it's really just very naive multitasking. I just boot up a bunch of processors. They're each doing their own thing, and they each need lots of RAM. So I think this case will easily fit into less memory once I'm doing, in the NTL version, I have much more control over memory. Sage, I don't have much control. And here's some running times, 3.5 hours for 1,000 and about 100, so what is that, 5 days for p equals 1,000,000. And you can see the square root of p is really quite apparent. In fact, it actually looks better than square root of p. So if I imagine that this was running on 12 cores and scales linearly, so this is only 60 hours. So that's about 3 times 18 hours, and 18 hours is about 3 times 7.5 hours, and so on. And it's actually looking worse for smaller p because of this other term that I mentioned. There's this other stuff which doesn't scale like square root of p. And just to put this in perspective, you think about how you would do this otherwise using some kind of naive point counting. So you've got to compute something like 10 coefficients of this, which means you need to count points on this surface over up to fp to the 10. So if p is 1,000, so how do you do this? So we're in p3, so I guess let's take an affine piece of this surface and count points on that. So I need to loop over two variables, say x and y, and then for every x and y, I plug it in, I get a quartic polynomial in z, and then I have to count the number of roots. So let's assume that's O of 1 time to do that. So you get an algorithm which is p to the 20, which is obviously not feasible for these size of p. I mean, maybe for p equals 2 you can do that, and for p equals 3 you can think about it, but pretty soon you can't do that. And these p are far larger than any p I've seen for any point counting problems in high dimension. I haven't seen any examples more than about p is like 29 or something like that. Okay, here is another example, the same K3 surface, this time over a non-prime field, so over F23 squared. And this case, the code still works, but it's a lot slower because Sage doesn't have such good support for non-prime fields for various tasks, polynomials over non-prime fields and p-adic extensions of them, and so on. So I used 3 digits of precision, which was actually a mistake. I should have used 4 for this prime. But you can just pretend that p is 43, in which case 3 digits would have been OK. And we can scale up the time accordingly. So it took about 11 hours running on 12 cores. So it would have taken maybe twice that, a bit less than twice that. So that's doable. Again, I think NTL implementation, there won't be such a huge slowdown. We'll be able to handle much larger primes. OK, let me bump up the degree to degree 5. So now p of t is degree 52 polynomial. So there's a lot of coefficients there. So I did one example here for p 1009 and 2 digits of precision. And it took about, so what is that, almost 3 days running on 12 cores. And in fact, this precision is enough to determine the first coefficient, which gives you the number of points of this surface. Now, this is a really stupid way to count the number of points on this surface. What you should do instead is just count the number of points on the surface, because it would take less than a small fraction of a second. There's only something like 1 million XY combinations that you've got to plug in. So that's not what you want to do. What you really want to do is take n, I think, equal to 5. Well, I guess this is really 4 plus epsilon. It's coming from the Hodge numbers. And then I sort of booted it up to estimate how long it would take, and my estimate is about 47 days. So you can see this large capital N is really killing us. This n to the n term is what's going on there. So I think this can be made feasible, partly just a tighter implementation, and partly there's something I call the interpolation trick, which I'll hopefully mention if I have time at the end, which I think will make a big difference in this case. So the interpolation trick was something that I also used in my paper on hyperelliptic curves, and that saved a factor. It was either square root of g or g. I can't remember. In the running time there. Okay, so now I'm talking about a threefold. So I've moved up to a 3-dimensional variety, so degree 3 in P3. And here the degree of the polynomial is 10, so there's not so many coefficients. And here's one example I did for P is 401 and 3 digits. This is sufficient for the whole zeta function. In fact, this is the smallest prime for which that works. And it took about 2.5 days running on 12 cores. And I also tried starting at degree 4 in P4 a couple of days ago, and it was still running, so I killed it. It's actually kind of fun to try and kill one of these things because this process is running all the other processes, and I was very lazy with the multitasking, so you sort of have to get in there with the hammer and really kill them by hand. But you can see this already degree 4 in P4 is already a difficult problem. I don't know if that will become feasible. I'd like it to, but I don't know. And of course, degree 5 in P4 would be really interesting. That's a Calabi-Yau manifold. There are lots of people interested in doing that, but I think that might be a pipe dream, unless someone gives me a very big computer. Okay, so let me tell you about how the algorithm works. So it's based on this paper of Abbott, Kedlai, and Rowe, bounding Picard numbers of surfaces using p-adic cohomology. So this paper actually, a preprint was posted in 2005, but I think it only just got published recently. So the basic idea, most of what I'll explain is common to both algorithms, to the new algorithm and to the AKR algorithm, and then I'll explain what changes need to be made to get this improved running time. So there's a formula for this P of t. It's a characteristic polynomial of Frobenius, so sigma q is the qth power Frobenius, acting on some rigid cohomology space. So here u is a complement of x in projective space. So now x had dimension n minus 1, u now has dimension n. So that's unfortunate that we're now working on an n-dimensional variety, but that's just life. This 1 over q, that arises from the fact that we've moved from x to the complement. That's what turns out to be the right modification. But apart from that, it's essentially a characteristic polynomial of Frobenius. So what is this rigid cohomology? The definition is complicated, and I don't pretend to understand it entirely. But in this case, it's essentially Monsky-Washnicza cohomology. So this is a p-adic analytic Durham cohomology. It turns out that this rigid cohomology space is isomorphic to this algebraic Durham cohomology of a certain p-adic lift of u, which I define as follows. I take my defining polynomial f, and I lift it p-adically to zq. Any lift will do, as long as it's the same degree. And then I lift this complement u. I call that u-twiddle. So here's a coordinate ring. It's just essentially rational functions which are allowed to vanish, allowed to have poles along this variety. So there's an explicit description of this Durham cohomology due to Griffiths. He was working with complex analytic varieties, but as AKR point out, the description works perfectly fine in this setting too. So what you do is you write down this certain n form, omega, some n form, and then this Durham cohomology is a quotient of two infinite dimensional vector spaces. So the first space, you just take all, so these are the cocycles. These are all forms g, so g is some polynomial in the x variables, and you divide by some power of f, some pole, so it has some pole along the variety. And you have to make sure that the degrees match up. You want the degree of this whole thing to be 0. So degree of f is d, and the degree of omega is whatever it is, n or n plus 1. I think it's n plus 1. So you take this space, and you quotient out by some relations. These relations, this is what makes it Durham cohomology. We're saying exact forms are 0. So this is an exact form. That some calculation needed to show that. So there's a form for every g, and for every variable I. There is one of these forms. So they're generated, if you just take g to be a monomial, they're generated by all of those. And the point of this is that this term here has a pole of order m plus 1, but this term has a pole of order m. So if you have a differential, and you can write it as a sum of terms like this, then you get to reduce it to terms like this. You get to reduce the order of the pole. And we'll see that's the main idea of the algorithm. So it's a finite dimensional vector space, and we can compute a basis just by linear algebra over ZQ. I said Z. I've been trying to say Z. I just said Z. I promised my new Australian friend that I would stick to Z. Okay. My apologies. Okay. Here it's okay, right. So here is what the basis differentials look like. I have x to the w, so this is with this multi-index notation. So some monomial divided by some power of f. They all look like that. And m is very small. M is, I think, less than n or n plus 1. So m is small. And so the number of these guys will be the degree of the polynomial p. So for the K3 surfaces, for example, there'll be 21 of these guys. So we can find a basis. Then there's a reduction algorithm. So what you do is you start with any differential like this, with a given pole order, and you repeatedly subtract off the relations, as I alluded to a moment ago. And you eventually find this guy in cohomology is represented as a linear combination of these basis elements. That's what it means to be a basis for cohomology. And we call this the reduction of this differential. And of course, it depends on the basis that you choose. Okay, so far I've only been talking about the cohomology. I haven't talked at all about a Frobenius action. So here is a Frobenius action. So there is a Frobenius action on this space. It's induced from sending, this is an absolute Frobenius, so it's induced from sending each x to its pth power. And that forces what the image of 1 over f has to be. It's given by some geometric series. So this is reminiscent, if you're familiar with Kedlaya's paper on hyperelliptic curves, it's sort of the same calculation. By some p-adically convergent power series. This doesn't make sense in the ring of functions on this space I gave you before. You have to work with a weak completion where these convergent series exist. And it turns out that then if you apply Frobenius to one of these basis differentials, so what happens? So this x becomes, the exponents are multiplied by p. you figure out the image of omega. It's some short calculation to figure out what that looks like. And then this image of 1 over f to the m is also given by some convergent power series. And what you end up with is a sum of terms of the following type. I won't write out the whole calculation, but you get a sum of these terms. And you notice that the variables always appearing to the pth power, with this little unimportant -1s, they're appearing to the pth power, and so is the denominator. So everything is these pth powers. And this is the first place where this algorithm diverges from AKR, because they used a different power series expansion, which was dense in all of these variables. And so it had at least p to the n terms. But it turns out if you're careful about how you write this power series, you can write it like this. And by the way, this means that the running time of the AKR algorithm is actually something like p to the n. They didn't give an analysis. They were just doing experiments with applications to coding theory in their paper. Okay, so now I can summarize roughly what the algorithm is. So first of all, computer basis for this cohomology. That's just some linear algebra. Lots of monomials flying about everywhere. Second, compute series approximations for the images of the basis elements under absolute Frobenius. And here I'll mention that the number of terms you need to get precision n in the final result is this n to the n. That's where this is coming from, because we need this many terms. Once you have these series approximations, you want to express them in cohomology as a sum of basis elements. So that you use this reduction algorithm to reduce to the basis elements. And this gives you the matrix of absolute Frobenius acting on this cohomology space. So again, this matrix is fairly large. In the case of a K3 surface, it's a 21 by 21 matrix. And then fourth, you multiply. If you're working with a qth power, so you're not working over a prime field, then you have to multiply this matrix by its conjugates to get the action of the qth power Frobenius. And then its characteristic polynomial is p of t up to some power of p and after some normalization, so scaling the variable by some power of p. Okay, so far it's pretty similar to what AKR did, and now I want to explain the main new thing that's different. It's something I call controlled reduction, and the idea is that when you do this reduction, you have to be very careful. So if I go back to this term here, so this sort of looks like a single monomial times omega, and I think of these monomials as living on an n+1 dimensional lattice. And these coordinates, p times u0 minus 1, are like the coordinates on this lattice. So we have so here's the origin. We're trying to get down to the origin. That's where the basis elements live, near the origin. I've got some point out here in this lattice, which is a single monomial. And if you apply this reduction algorithm that I mentioned before without taking much care, then it starts spreading out into, as the pole order goes down, you come towards the origin, but the number of terms starts increasing. And in fact, the number of terms increases roughly as the nth power of the distance you've traveled. It sort of spreads out like this in a cone. And that's bad. What we want to do somehow is starting with this single monomial, we want to reduce to just a small cluster of monomials and keep reducing without increasing the number of terms. That's what this controlled reduction does. So I'm going to consider a differential of the following type. So G here is a polynomial of small degree. The degree is a number beta, which turns out to be dn minus n. So for example, for a K3 surface, it's 4 times 3 minus 3 is 9. So a polynomial of degree 9. And x to the u is the sort of base point of this cluster of differentials. So what this differential looks like on this lattice is a base point x to the u and then a cluster of terms nearby. That's given by g. And what I ultimately want to do is reduce it to something like this. So x to the u, the base point has shifted over by x to the v. So in my head, v stands for velocity. It's the direction that it's traveling. X to the v, and some other polynomial g prime, and a correspondingly lower pole order. And once I can do this, I can iterate. And then that's the controlled reduction. So I can do this. I'm going to choose a monomial x to the v of degree d. That's the direction I'm going. And for this discussion, I'm just assuming that S is empty and that all the UIs are not too close to 0. Otherwise, things get complicated. So in general, the smoothness condition is what guarantees there is some x to the v for which this controlled reduction will work. But if you assume that S is empty and all the UIs are not close to 0, then you can choose any direction you like. And then you get the state. So this is the main technical result that makes the theorem, that makes the algorithm work, is that you can do this. It's some calculation just with lots of monomials and partial derivatives and so on. Now, I don't want to explain in general that calculation because it's not very illuminating. What I'll do instead is show you a special case, which I only realized a few days ago when I was preparing this talk, that this works. And it actually helps explain a little bit where this dn minus n comes from, which is otherwise a little mysterious. So let's take the example of a diagonal hypersurface in P3. So a very simple equation. Just the sum of the fourth powers of the variables is 0. Now suppose we have this differential and we want to reduce it in the direction x to the v, which is x0, x1, x2, x3. And in fact, this is the only choice we can use in this case because I'm going to assume here that S contains all the variables. So in that case, that's the only choice you have. But it's certainly smooth, so everything's fine. Okay, what I'm going to do is now, so I've got this differential, and all I need to do is show how to reduce each term in this differential. So I'm going to pick a typical term, x to the w, given by this exponent vector. And the sum of the wi's has to be 9. That's the degree of g. And this is a crucial point. This is just some kind of pigeonhole principle. At least one of the wi has to be greater than or equal to 3. Because if all of them were less than 3, then the degree could be at most 8. So it forces one of the variables to appear with multiplicity 3. Let's call it wj. And once you've chosen that variable, then you have to do some calculation. So you start with, this is the term I'm trying to reduce. And I pull out this factor of xj cubed out of x to the w. Now here, this indicates cohomologous, this little twiddle. So then I apply my reduction relation. This turns out to be what you get. You get this 1 over 4m minus 1, partial derivative of this stuff. And so that pole order should have been reduced. So something's gone wrong, but let's just pretend that's m minus 1. And now you do some undergraduate calculus to take this partial derivative. And you get uj plus wj minus 3. That's just coming from these exponents. And then the product of these terms. Now I have xj to the minus 4, but I've grouped it so that this term here is a polynomial. And this term here, you see I can pull out a factor of x to the u minus v, because all the other variables, I just pull out all the variables except for x to xj. And this is what I get. So this calculation is showing how the controlled reduction works in this case. And the point is that for each term in G that you're trying to reduce, you have to use a different relation. So you've got this bunch of terms, and the terms that are in that direction, in the x0 direction, if they have a high power of x0, you have to use a relation that gets rid of x0s. And if you're in this direction, you might have to use a different one. And so what happens for the general case is you have to do some commutative algebra to show that you can always find relations that will do what you want. Now, if you put all of this together, I've told you so far, you get an algorithm with the following running time. P to the 1 plus epsilon, actually maybe even, no, not p to the 1. P to the 1 plus epsilon, something polynomial in the input size, and this n to the n. So the n to the n is the number of terms I had to reduce. This polynomial comes from just the size of the matrices. I have the size of the number of terms I have to deal with in the reduction. And the p is coming from the fact that I had this lattice of differentials that were spaced by p, and I just sort of reduce along the lattice direction. So I start here and I go p steps, and then I go p steps, and I go p steps until I get down to the origin. So this is where this p to the 1 is coming from. So the last question is, how do I get from p down to square root of p? And actually, once you've formulated the problem like this, it's actually not that hard to see how to do it. So if you look at this reduction, so imagine I reduce in the direction v for many, many steps, for about p steps. So I start off with x to the u minus lv, and I reduce to x to the u minus l plus 1v. And I do this for L equals 0, 1, 2, 3, 4, etc. up to P. If you look at what you're actually doing, you're going from G to G prime. So it's a linear map going from G to G prime. That's not hard to see. So let's write V beta for the space of polynomials of degree beta. This is where G and G prime live. So I'll call that map R U comma V of L. So it's a linear map. But the more important thing is that if you write down a matrix for it, the entries of the matrix are degree 1 rational functions of L. This is just what they happen to be. And all the denominators are the same. So let me just go back to this slide, and so you get a feeling for why that's true. So here I'm reduced. This is one reduction step from x to the u down to x to the u minus v. Now if u, so u is moving in a line. The exponents are parameterized linearly with L. And so is this m. This m, which should be m minus 1, is also parameterized linearly by L. So this coefficient here is a rational function of L, a rational linear function of L. This uj is linear in L, and this denominator is linear in L, and everything else are constants. Now, what that means, so once I know this has that form, so what I need to do to reduce all the way from here p steps, I basically need to multiply these matrices together. I need to do the first reduction step, the second reduction step, all the way to the pth reduction step. And for matrix products of this type, there is a fast algorithm of Chernovsky. I think it's from a different paper than the one everyone's been talking about. I have to check that. With some recent improvements by Bostan, Godry, Schost. So this algorithm depends on fast polynomial arithmetic, and it can compute this matrix in about square root of p steps, rather than the naive just multiply out the matrices. In that statement, I'm ignoring the size of the matrix. And to give you an idea of how big these matrices are, for the K3 surface, the matrices are 220 by 220 matrices. They're already quite large. These are matrices with p-adic entries. So 220 is the number of monomials of degree 9 in 4 variables. I think that's what it should be. And so for the Calabi-Yau case, the degree 5 in P4, the matrices are something like 5,000 by 5,000. So that's getting kind of scary. That's already making life very hard. So I'll finally finish with a couple of open questions. So the first is, can we get any traction from this interpolation trick? So what is this trick? It's the following observation. If you take this product of matrices that I just wrote down, that actually, if you fix v, you fix the reduction direction, this varies p-adically analytically with the coordinates of u. Now, what I mean, so for example, if I just look mod p, what that's saying is all the reduction matrices mod p are the same, right, for a particular direction. So to get from here to here, it looks the same mod p as to go from here to here, as long as you're going the same direction. For different directions, it's not true. I don't think they have anything to do with each other anymore. But what that means is you don't need to compute so many of them. For instance, suppose you want to know these matrices mod p squared. Then, so you write down a Taylor series expansion of this gadget in the coordinates of u. And so you've got a constant term. And then if you want p squared, you need all the linear terms in all the various variables. So you only need n plus 2 of these instead of all of them. Then you can compute all the rest mod p squared by linear algebra. And in particular, that extra calculation doesn't depend on p very much. So I don't know how much this is worth in general. The main difficulty is I don't know how much precision I need. What I can prove is a little bit distant from what actually seems to work. And the same thing happened with Kedlai's algorithm, except that here I don't even know what to conjecture. For the hyperelliptic case, I was able to write down exactly the power of p that is supposed to divide these things. And in this case, you try to write down the natural generalizations of those statements, and they're just false. There are extra p's in the denominator, which shouldn't be there. So I don't know exactly how to do this. I studied the K3 case, so degree 4 in P3, and in that case, I think you can save a factor of about 2, which is not as much as I would expect, given the precision is so low. The problem is that there are so many different reduction directions you need to consider. You start off with lots of monomials out here in the interior of the lattice, and you start reducing them, but you start hitting the boundaries. And when you hit the boundaries, you need to change direction. And it turns out you need a lot of different directions. And so you can only use this trick once for each direction. So that doesn't help. But for higher degree, I think there will be more gain, because there are just a greater proportion of points are out in the middle of this lattice. So I think that will help. The second question, which I guess is even more important, is can we combine this algorithm with deformation techniques? And I don't know enough about deformation techniques yet to really have a good answer for that. So one question, can we run Lauder's algorithm in square root of p time by using a trick like this? I don't know. Or even can we improve the p squared down to p to the 1? I think he mentioned in another paper that he conjectures it can be done in p to the 1 time, but I don't know. If you combine these techniques, could I get down to polynomial time in the input? And I guess the idea would be that you'd start with your surface, you'd deform to a diagonal surface, you'd run this algorithm, which somehow might run better for a diagonal surface because of the sparsity of everything, and then maybe you would be able to recover that running time. I have no idea. And thirdly, related to this, are there any systematic improvements for surfaces with sparse equations? So does this algorithm actually run better for a diagonal surface? It seems to. When I run it, it's faster. There are just lots of extra zeros everywhere, but it would be nice to analyze that and really understand what's happening. And I should mention also, John Voigt has done some, I spoke with him a few months ago. He has an algorithm which is kind of related to this one, we think, which only works for equations that are sufficiently sparse. So interesting to look at that and see if we can learn anything from that. And then I just want to drop various conditions. Can we drop this annoying extra smoothness condition? I mean, geometrically it's a bit strange. I don't know what it means. Maybe I'm just missing something in the algebra. Maybe there's some way to rearrange things so that you don't need that extra smoothness condition. What about smooth affine varieties? This is actually the problem that I started with. I thought when I had this idea, I was trying to do this first, and then I went and spoke to Karan, and he said, I'm crazy, I should do projective ones, and he was right. Smooth affine ones, if the projective closure is not smooth, then it's very hard to describe. It's very hard to sort of get a finite dimensional reduction problem. Complete intersections should work. I don't think there should be much problem here. Weighted projective space, probably also okay, but I don't have to think about what the cohomology looks like there. And finally, can we drop smoothness altogether? This leads to funny stuff happening with cohomology, but I should mention that the algorithm of Lauder and 1 from 2000 doesn't require any smoothness conditions. So maybe looking at their algorithm, we could figure something out. Okay, that's it. Thank you very much.
All right, any questions? Yep.
Have you tried running this on any curves that you couldn't have handled with your
Oh, I have actually run it on curves. It's a lot faster than this, but I mean, it's not remotely competitive with any algorithms designed for curves. I mean, this isn't actually a generalization of the hyperelliptic curve case, because for hyperelliptic curves, the way they're embedded in projective space is not smooth. So it's not exactly a generalization. But it is interesting that it works for such a wide variety of surfaces. But I haven't really thought about it too much for curves. No.
Also a question myself. Is there an easy way to check the correctness of your answer?
That's a good question. So to be totally honest, I haven't actually checked the correctness of any of the output from this implementation. What does happen is the answer that you get for this implementation anyway is obviously a Weil polynomial. Right? I mean, it's p-adically very close to something that you can check that the roots have the right size and so on. I did check several of the examples from the first implementation. In that case, it's hard to check the whole thing, right? Because what do you compare against? There isn't any other way to do it. So I checked the first 1 or 2 or 3 coefficients for the smaller p that I could. And they were all okay. And it also was a Weil polynomial. So some people suggested you could do things like you write down a surface where you have some other easy point counting algorithm, and then you just do a random rational change of coordinates and run this algorithm on it and see if you get the same answer. And you should. But you don't really know, is it somehow using some secret structure that... So it's a hard problem, actually, testing an algorithm like this. Apart from those ideas, no, there's nothing else I can say.
All right, if there are no more questions, then let us thank all speakers of the afternoon.